This sprinter starts from rest and starts at a position of 0 meters, x naught, the initial position, and 10 seconds later has moved to a position of x equals 100 meters. So from this information alone, we can calculate the average velocity of this sprinter. And this one's not exactly a brain teaser, but the average velocity is the displacement over the time. Delta x, the change in position. Well, delta, the change, is defined as the final value minus the initial value, x minus x naught, over t minus t naught. So we see that x is 100 and x naught is 0, t is 10 seconds, and t naught, the initial time, is 0. So 100 meters minus 0, 10 seconds minus 0. We know that this is 10 meters per second for the average velocity of this sprinter. Now, you can see a couple of things from this. The first one is why we usually don't worry about t minus t naught. We simply call this the elapsed time, and we know that it's 10 seconds, and 10 is what we put there. And for the change in position, obviously, if you started at the position of 0, all you need is the final position, 100 over 10, 10 meters per second. But the point here is that delta means final value minus initial value. What this does not tell us is what was the velocity of the sprinter 2 seconds after they began, or 5 seconds, or 8 seconds after they began. In order to know that, we need to know what was the rate of change in this runner's velocity. So if they started from rest, well, we know that their initial velocity is 0. That's what starting from rest means. 0 meters per second, but we have no idea what the final velocity was. V final is a complete unknown, but if we knew the acceleration, we could find it. So acceleration is defined as the rate of change in velocity. A rate means over time or per unit time. The change in velocity, well, we know that delta means change, so acceleration is defined as the change in velocity over the elapsed time. So we know that delta is v minus a v naught, final velocity minus initial velocity, and for the time, think of your stopwatch and starting from 0. Why don't we just put a t there and call that t? And so this is how we define acceleration. It is the rate of change in velocity. And if I manipulate that equation just a little bit, if I take a as v minus v naught over t, and I solve for v, I find that v is v naught plus at. This is one of our equations of motion. You need to know this. Commit it to memory. There is a series of videos on YouTube called Don't Memorize, I think. Yeah, that guy's crazy. Memorize away. You have a most outstanding brain that is very good at storing data. It seems silly to me not to make use of it, particularly in light of the fact that you will need to take a timed exam. If you think you're going to derive every equation you need on the spot, there is not enough time to do that. Memorize. There's nothing wrong with memorization. V is V naught plus AT. The final velocity is the initial velocity plus acceleration times time. Now, if we take a look at the units for acceleration in the metric system, the acceleration being the change in velocity, well, we know that velocity is meters per second. So just look at this part here. We know that the change in velocity is measured in meters per second over time, which is in seconds. So we have meters per second per second. This is the change in velocity in meters per second each second. Meters per second, we usually just write that as meters per second squared. These are just units. Don't square a number. That simply means acceleration, the change in velocity in meters per second each second of elapsed time. And here's something really important. For our class, in order to make sure that this remains algebraic and does not require calculus, our accelerations are constant. Or let's say they are uniform. That means if I give you an acceleration of, say, 2 meters per second squared, it remains 2 meters per second squared throughout that particular part of the problem. If the rate of change in velocity is not uniform, that requires calculus.